Okay. Hi, my name is Trevor. Thank you for having me back. I'm a software developer at Expedia. I have a Bachelor of Science degree with an electronic arts with an emphasis in video studies, and I minored in computer science. But for brevity, I just tell people that I was a student filmmaker. Likewise, a more accurate title for this talk would have been Computer History with an emphasis in software, but Software History 101 sounded better to me, so that's what we landed on. I've never heard of a software history class before, and I think this is going to be a more studied topic in the future. Having learned the art of storytelling in college, I hope to use my talents to tell a comprehensive, coherent story of how we got to the modern world of software. Sadly, I'm going to have to skip some great stories in computer science, history, otherwise we'd be here until midnight, but we still have a lot to get through, so I'm going to have to talk quickly and loudly. Welcome to Victorian England. It's the beginning of the Industrial Revolution, and already mechanical calculators like slide rules are being used to do simple math such as addition, subtraction, multiplication, and division. For anything more complicated, for example, if you were a scientist or an accountant or you were needing to navigate a ship at sea, you would need to buy a book of calculation tables for things like logarithms, sine and cosine, and polynomials. The people who performed these calculations and made these books were called computers, most of which were women. Because these books were calculated and written by humans, they had plenty of errors. So one day in 1821, a 29-year-old well-respected mathematician named Charles Babbage said, "I wish to God these calculations had been executed by steam. After all, machines can do physical labor accurately and tirelessly, so why not mental labor?" He had a solution to create a machine that could calculate up to sixth-order polynomials, and this machine repeated additions and subtractions through the method of finite differences, so he called it the difference engine, and this is a small demo of that. So looking at this thing as a user, you would have 6 20-digit inputs in base 10, because that's the most intuitive thing, each representing one of the leading coefficients of your polynomial, and as you crank the machine, it will iterate through values of x to compute f of x, which you could write down in your calculation table. And this is what the equivalent C++ code would look like, just to give you an idea of the complexity. It cannot be stressed enough how alone Babbage was in pursuing this idea, but he managed to secure funding from the British government to build the difference engine. Babbage was a socialite among the nobles of Victorian England, and as such, he attended and hosted parties where he would talk about and show off his inventions, but a lot of people had a difficult time keeping up with him and sharing his enthusiasm for these highly specialized calculating machines. At one of these parties, he meets a 17-year-old, well-educated girl named Ada Byron, but you probably know her better by her married name, Ada Lovelace. Lovelace not only keeps up with him in conversation, but stands out to him as the only person who really understands the potential of his ideas. This is an illustration from a book that sort of tells the story and then tells an alternate universe story. Babbage shares with her larger ideas he's having about the kinds of math operations a machine can perform. Now, because the design of the difference engine is so complex and requires hundreds of machine parts with narrow tolerances, Babbage repeatedly misses his deadlines for the difference engine, but manages to convince the British government to continue to top up his funding, and all the while he's envisioning a more advanced machine that can do a lot more than calculating polynomials. Babbage has an idea for a general-purpose machine which could accept a sequence of instructions in the form of holes punched into cards to perform any mathematical operation, and all you had to do in order to change what you were computing was feed the machine different instructions. This unique machine is what Babbage called the analytical engine. It was comprised of a store, which is that long part over there, where numbers would be retained, and a mill where the numbers were like crushed and ground together like a cotton mill or a flour mill. It had 3 inputs given to the machine in the form of punch cards. It had variable cards describing memory addresses of variables in the store, number cards describing the initial values for the variables you were computing with, and operation cards, the instructions. Amazingly, this machine was going to be capable of loops and conditional branching 100 years ahead of its time. The idea was it can compute anything. Charles Babbage bounced all of his ideas off of Ada Lovelace. Ada Lovelace was very good at communicating his ideas to a broader audience and expanding upon them in unique ways. She famously published an algorithm for the analytical engine that would compute the Bernoulli numbers, which had a mysterious and esoteric reputation among mathematicians at the time. This was the first formally documented computer program, which, keep in mind, was written for a machine that didn't even exist and, in fact, would never exist. She even had the foresight that if you could assign different meanings to the numbers you give to the computer, the machine could even produce creative work, like music. Unfortunately, Ada Lovelace died young, and Babbage grew old and bitter at the world for never understanding his great machine. But his ideas lived on in the minds of mathematicians. In the modern age, a museum curator named Doran Swade managed to build the difference engine, demonstrating that Babbage's designs were exactly correct, even though it required precision machine components that weren't possible during Babbage's lifetime. Doran Swade is currently working on deciphering Babbage's notes to reproduce the analytical engine. So after Charles Babbage's death, time passed, the power of electricity was harnessed by humans, and a new dawn of computing began in the 1930s. Innovation is about to occur simultaneously, independently, but also collaboratively across the world. From here on, the people and contributions get so tangled that it's difficult to draw a straight line through the story, but we're going to try. We're going to start with a young math student at Shelbourne School in England named Alan Turing. And Alan Turing shares a fascination of science and math with his first love, Christopher Morcom. Morcom tragically dies young, and this crushes Turing, but it also lights a fire under his ass. In a note to Morcom's mother, Turing wrote, "I know I must put as much energy, if not as much interest, into my work as if he were alive, because that is what he would like me to do." So Alan Turing focuses on solving a fairly new mathematical challenge called the Entscheidungsproblem, translated from German as the decision problem. The Entscheidungsproblem goes something like this. Is there a step-by-step process that you can use to determine whether any given logical statement is true? And so Alan Turing puts his nose to the grindstone to prove it one way or another. And in 1936, as a fellow of King's College, he writes an inspiring paper called On Computable Numbers. And the core idea of this paper is simple. It's just what numbers are computable and what numbers are not. In this paper, Turing mathematically describes a machine with similar properties to Babbage's analytical engine, which he calls an automatic machine, but today we know it as the Turing machine. Unlike Babbage, Turing doesn't dive into the details of how the machine works mechanically. He just describes what it does. A Turing machine is an abstract theoretical device that operates on a tape with a list of numbers on it. Doesn't necessarily need to be ones and zeros. And before you start the Turing machine, you also give it a bunch of instructions for how to operate, which is like the mechanism in the middle there. When the Turing machine is running, it's only ever going to be looking at a single number on the tape, and based on the number that it's currently looking at, it will follow the instructions and do a sequence of primitive operations. The Turing machine only needs to be able to do 6 primitive operations. Read a number, write a number, move one step to the left, move one step to the right, change state, and end. And from these basic operations, you can provide instructions that make the machine do addition, subtraction, multiplication, and division. With this simple idea of an automatic machine, Turing not only proves the Entscheidungsproblem has no solution, he also proves that there is a vast set of numbers that lies beyond what any mechanical procedure can ever compute. There is no machine that you could make that could calculate something that a Turing machine cannot. Any machine that can emulate a Turing machine is therefore able to compute anything a machine can possibly compute, and so therefore it's considered Turing complete. And you should know that right before Turing released this paper, a different mathematician named Alonzo Church, entirely independently, proved the same thing in a different way using a mathematical tool he invented called lambda calculus. But Turing's solution ended up being more influential because it described the kind of real step-by-step process the Entscheidungsproblem was asking for. So you may have noticed, but step-by-step process doesn't exactly roll off the tongue, and it doesn't really sound like a mathematical term. So Turing, Church, and other mathematicians adopt a new word, algorithm, named after a Persian scholar from the Islamic Golden Age named Al-Khwarizmi. Notably, Al-Khwarizmi wrote a book called Al-Jabr, which we now call algebra. So now we have an idea for a machine that can conceivably run any algorithm, but how do we build it? Well, while the mathematics community is talking about Turing's paper, a student of electrical engineering and mathematics at MIT is in his own world toying with electrical relays, and his name is Claude Shannon. Shannon spends his days as a research assistant operating on an analog computer called the differential analyzer, not digital, analog. This machine was capable of solving differential equations by rolling a ball over a spinning disk to drive a pen to draw a curve on a piece of paper. It was invented by his boss and mentor, Vannevar Bush, and it has about 100 relays in it, not for actually making the pen draw the line, but for routing power and switching machine states and such, like auxiliary things. At the time, relays were really just a communications technology used by telephone companies, not a computation technology. So Shannon spends months starting the differential analyzer up, monitoring it, troubleshooting it when it screws up, and optimizing the relay circuits. And as he's working on this machine, Shannon realizes that the behavior of the circuits can be perfectly explained by Boolean algebra, which is the study of combining true and false statements created by a not very well-known mathematician named George Boole. When Shannon realized that he could express the relays in writing and then use that mathematical language to simplify a real circuit, he showed Vannevar Bush this kind of process, and Bush immediately recognized this as something very practical and useful, and he enthusiastically encouraged Shannon to formalize these ideas into a master's thesis. So in 1937, only a year after Uncomputable Numbers was published, having no knowledge of Alan Turing, Shannon writes a symbolic analysis of relay and switching circuits, which became known to many as the greatest master's thesis of all time, and also as the birth certificate of the digital revolution. And at the same time Alan Turing and Claude Shannon were doing their theoretical work, a physicist at Harvard was dreaming of a machine to automate the tedious calculations he had to do as a doctoral student. This is Howard Aiken, and he managed to secure funding for a digital computer with the one and only International Business Machines, IBM. Thomas J. Watson Sr., IBM's powerful and famously ego-driven chairman, agreed to fund the machine since he thought the partnership with Harvard brought legitimacy and prestige to IBM. So Aiken works with manufacturers for years to manufacture and assemble all 750,000 parts of this new machine to be named the Automatic Sequence Control Calculator, or the ASCC. After a couple of years, World War II breaks out, and Aiken is called into active service as a U.S. Naval Reserve officer. And the Navy sees the value of the machine that he's building for missile trajectory calculations. So they assign him to continue to oversee the completion and operation of the ASCC. And after a few more years, in 1944, Howard Aiken and IBM finally finish building the ASCC, and they invite IBM and Thomas J. Watson Sr. to a dedication ceremony at Harvard for the new machine. Now, we don't have all the details. Maybe it was the Navy's influence. Maybe Aiken had personal differences with IBM engineers, and maybe Aiken was just a jerk, who knows? But at some point, Howard Aiken became insistent on calling the ASCC the Harvard Mark I. And neither Harvard nor Howard Aiken gave much credit to IBM for their funding or manufacturing. The dedication ceremony was apparently disastrous. Watson left deeply offended, and although audio recordings of the event do exist, they were buried in the university's archives and labeled as fragile. The fallout would push IBM to design and build their own computers and shape the business world in the decades to come. Now that the newly named Harvard Mark I was built, the Navy sent Aiken a team to help operate it, including an impressive woman with a PhD in mathematics named Grace Hopper. The Mark I was programmable, but it couldn't do conditional branches, so no if-else logic or looping behavior, so it wasn't Turing complete. But at 51 feet long, it was huge, and it was built with relays, wheels, and switches, so it was loud, but it was powerful. It could do 3.3 operations per second on 72 23-digit numbers in base 10. Again, base 10. It ran 24/7, calculating all sorts of things for the war effort. Funny little side story. In the summer of 1947, the team were working on a new computer called the Mark II, and because it was hot out, they left the windows open. And for some reason, the Mark II stopped due to a failing relay somewhere in the system. So they found the relay in question, and they see that it's blocked by a poor little moth that had been repeatedly hammered by opening and closing. So they taped it inside of a notebook, and there they wrote the first actual case of a bug being found. And a lot of people think this is where the term bug comes from, but that was actually Thomas Edison's invention. So one day, a Hungarian man shows up to see the Harvard Mark I, a mathematician, a physicist, a computer scientist, and an engineer, all wrapped into one. His name is John von Neumann, and he's widely regarded as one of the smartest people to have ever lived. At 6, he could perform mental arithmetic for eight-digit division in his head. He's there from the Manhattan Project, and he needs to run some calculations to see if this idea of imploding the outer shell of the atomic bomb will trigger the atomic chain reaction in the middle. This serves as a convenient segue into the first entirely electronic computer. The Harvard Mark I was the US Navy's computer, and likewise the US Army wanted a computer of their own. So they funded the construction of a new computer at the University of Pennsylvania designed by an engineer, J. Presper Eckert, and a physicist, John Mauchly. This computer was to be called the Electronic Numerical Integrator and Computer, or ENIAC for short, and John von Neumann was a consultant on the project. Unlike the Harvard Mark I, the influence from Turing and Shannon here is clear. It was the first Turing-complete computer, and instead of relays, it used vacuum tubes. Compared to the Mark I, this thing was fast. It could do 5,000 operations per second compared to the Mark I's 3.3. The programming team consisted of these 6 women. It was around this time that a new term started to be used to describe the native size of a number that a computer could operate on, a word. Similar to how a word is the basic unit of spoken language, a word in a computer is the basic unit of data, and the size of a word in a computer tells you how big of numbers it works with. Anyway, the ENIAC was operational only a year after the Harvard Mark I in 1945. The way you programmed it was weird, though. You had to physically unplug and plug in wires to set up the computation that you wanted to do. Now, notably, Howard Aiken was adamant that the data and program instructions were to be stored separately from each other. Aiken believed philosophically and practically that a program is not the same kind of thing as data, and that conflating them was conceptually wrong and potentially dangerous. This became known as the Harvard architecture. But von Neumann, Eckert, and Mauchly had a different idea. What if you stored your program in the machine's memory with the numbers? It would make the computer more general purpose. You wouldn't need to physically rewire the machine to run a different program. And using a single high-speed memory component for everything would make it simpler and faster. This idea is called the stored program computer. Von Neumann wrote this in a summary of the next computer they would build called the EDVAC, and the scientific community read it and dubbed his version of the stored program computer the von Neumann architecture. Controversially, Eckert and Mauchly had also come up with this idea, but von Neumann was more popular and his name was the one on the document, so he got the credit. The idea was so successful that practically every computer today is a von Neumann architecture computer. And there's the difference between Harvard and von Neumann. Finally, in 1945, World War II ended, and now that the Allies had funded the pioneering computers for the war, the business sector was about to take off. I've already introduced one of the major players, IBM. The other is the massive telephone monopoly, American Telephone and Telegraph, AT&T. But more specifically, their well-funded research branch, Bell Labs, whose mission was to provide freedom to their researchers to pursue any line of inquiry as long as it might one day contribute to their communications system. In 1947, Bell Labs created the transistor. The transistor is a borderline magical electrical engineering component because unlike relays and vacuum tubes, it has no moving parts and it doesn't wear out with use. And it can be manufactured at really small scales, which allows computers to become smaller and faster and more reliable. Here we meet a familiar face, Claude Shannon. Since we last saw him, he got his PhD in mathematics. He did some groundbreaking cryptanalysis for the US during the war, and now he works at Bell Labs. Shannon decides that the greatest master's thesis of all time isn't his final word, and in 1948 he writes a new paper titled A Mathematical Theory of Communication, creating an entire new field of research that we now call information theory. Information theory is the foundational science behind modern encryption, compression, the internet, and basically everything that makes the modern world the information age. And this is also where we get the term bit, as a contraction of the words binary and digit, the smallest measurable unit of information. While all of this is happening, universities and institutions around the world are building their own computers. I'm talking MIT, Princeton, Manchester, Cambridge, and many others. And each of these new computers has its own capabilities, its own set of instructions, and its own unique notation and writing, which people start to call assembly languages. At this time, Grace Hopper has since left the Navy, and she now works with who else but Eckert and Mockley as a programmer at their new business-facing computer company, the Eckert-Mockley Computer Corporation. As they're working on their next big computer called the UNIVAC, she's realizing that in order to write a program for any single computer, you need to learn all of the operations that the machine you're working with is capable of. And she's also realizing that programming is just more difficult for people without a background in math. So she devises a language for describing computer algorithms that doesn't just apply to one machine, but is high level and uses English words to describe what a machine is supposed to do more generally. She called this language Flowmatic. Of course, the Flowmatic language needed to be converted into the digital machine code which the computer actually needs to run. So they created a special program for the UNIVAC that would take the text of a Flowmatic program as inputs and outputs the machine instructions that you could feed right back into the computer. They called this special program that converted a high-level language to machine code a compiler. This is around the time the world started to refer to programs and data that make computers run software in contrast to the physical hardware. The Department of Defense took Flowmatic and, with guidance from Grace Hopper, created a successor, the Common Business-Oriented Language, also known as COBOL. Simultaneously, IBM was doing the same thing. After they got burned by the Harvard Mark I, IBM started building their own computers, and in 1956, they created a computer called the 704, but more importantly, they shipped it with their new programming language. IBM had independently conceived of a compiler, which they called a formula translator, which they shortened to name their programming language Fortran. It was becoming standard for programmers to use a machine to punch lines of Fortran or COBOL code into these IBM punch cards, which would be used until around the 80s. So you see more and more computers are being built, and new competing standards are emerging for programming languages. So in 1958, computer scientists and mathematicians across the world meet in Zurich, Switzerland, to create a common programming language that people can share and read and compile to a variety of machines. After 1 week of contentious debate, they emerged with a new universal programming language called the International Algebraic Language, or IAL. It wasn't perfect, but this was the programming language standard that introduced a lot of ideas that still exist in programming languages today, such as the idea of nested block structures and variable assignment syntax. The colon equals is supposed to look like an arrow pointing left. Most importantly, they came up with a way to specify what was correct versus incorrect syntax for IAL, which they called the Backus-Naur form, or BNF. In modern code editors, BNF files are used to check whether you've made a syntax error when typing code. It was recognized that IAL needed work. In particular, they hadn't come to a resolution on how to do recursive algorithms. So 2 years later, they meet back up in 1960 in Paris, and they decided they were going to make a new, better standard that addressed everything wrong with IAL. And because IAL was an unspeakable and pompous acronym, they called it ALGOL 60, and they renamed IAL to ALGOL 58. One of the members of the ALGOL team wasn't entirely satisfied with the language. His name is John McCarthy, and he had co-hosted a conference at Dartmouth College with Claude Shannon back in 1956. This conference was organized to discuss what seemed like a crazy idea at the time, artificial intelligence. Remember Alonzo Church? Inspired by the idea of AI, McCarthy decided to take Church's lambda calculus and use it as the basis for a symbolic programming language capable of human reasoning, which he called Lisp, which is short for list processing. This is how programming languages diverged into two paradigms. ALGOL was considered procedural and Lisp was considered functional. Instead of recursion being an afterthought, Lisp leaned into recursion as primary means of expressing repetition rather than loops. Lisp also pioneered several features still used today. Garbage collection, the idea that the programmer shouldn't have to hold the responsibility of managing computer memory. Dynamic typing, variable types that are flexible and checked while the program is running rather than when you compile the program. And homoiconicity, which is the abstraction of code and data as a single concept. Everything in Lisp, including the program itself, is a list. Wild ideas, but ones that, alongside ALGOL, would shape the future of programming languages. The world of software and programming languages is opening up, and just in time for the space race. Famously, in 1961, Kennedy announced that we're going to the moon, and suddenly a lot of the greatest minds in the US are put to work at NASA in pursuit of that goal. In one of the greatest superhero crossovers of all time, the US government pulls in MIT, IBM, and Bell Labs to help. NASA realized that they needed a computer aboard the spacecraft to assist with precise control of its trajectories and velocities and alignment during the most critical phases of the mission. And wiring transistors together by hand was not going to cut it. The computers at the time were simply too big and heavy. So instead, they pushed forward the development of a recently new technology that could etch an entire computer circuit, including all its transistors and resistors, onto a single lightweight piece of silicon. And this was the birth of the integrated circuit. If the transistor seemed magical, the integrated circuit was straight up science fiction. Once they had the hardware, NASA kind of just wiped their hands and went, job done, and the software was considered a less important implementation detail, so they shoved that off onto somebody at MIT. This is Margaret Hamilton. She had some experience in programming air defense systems, so NASA put her in charge of programming the Apollo guidance computer. She took this task very seriously. Margaret Hamilton pushed for a lot of software practices that are still used today, such as rigorous testing, error handling, systematic documentation. And although her colleagues joked about her radical ideas, she insisted that her department be called the Software Engineering Division. This is where the discipline of software engineering began. The best part of this story comes during the landing of the Apollo 11. Hamilton insisted for the Apollo guidance computer to use a priority-based scheduling system, which allowed multiple tasks to be executed asynchronously. If the computer ever got overloaded with too many tasks, this allowed the ones that were considered less essential to be dropped. As the lunar module descended to land on the moon, a faulty piece of hardware on the ship was overloading the computer with too many tasks. Inside the spacecraft, a program alarm went off and a mysterious error code appeared on the computer display. Mission Control back on Earth saw the telemetry coming from the spacecraft and questioned whether the landing should be aborted. But because the situation had occurred during testing and it was well documented, Mission Control realized the computer was behaving exactly as it should. And because of Margaret Hamilton's commitment to excellence, minutes later, humans stepped onto the surface of the moon for the first time. Also in the 60s, IBM was finding major success with their business computers. Punch card programming was becoming more and more widespread, and similar to the Apollo guidance computer, new time-sharing systems allowed multiple programs to be run at effectively the same time by switching between jobs at runtime. IBM started selling a new kind of computer for business-critical batch processes, which started being called mainframes, distinct in purpose from pure number-crunching supercomputers meant for scientific research. They had an estimated 70 to 80% market share, so more and more of the public were learning programming by writing programs on a stack of IBM punch cards and then taking them to their institution's computer clerk. The clerk would then put the programs into the computer and keep the printed logs for whenever the user returned. And I was able to consult my own parents about their experience with punch card programming, and their main concerns that I heard were you couldn't debug the program yourself. So if your program failed to run correctly, troubleshooting took a long time. If you messed up a loop and your program ran forever, you'd get charged a lot of money, or your program would be kicked out for taking too long. And God forbid you ever drop a stack of loose punch cards because it would take forever to get them back in order. These time-sharing systems and priority-based scheduling systems eventually culminated in an ambitious new operating system. co-developed by MIT, Bell Labs, and General Electric, the Multiplexed Information and Computing Service, abbreviated as MULTIX. It was meant to turn computers into a public utility, and it introduced a number of revolutionary features, such as hierarchical file systems, virtual memory with segmentation and paging, dynamic linking, a security system that separated user code from supervisor code. Unfortunately, MULTIX, ambitious as it was, became a victim of its own complexity. It was bloated, slow, and expensive to run, and by 1969, Bell Labs had seen enough. They pulled out of the project entirely. But two of their researchers, Ken Thompson and Dennis Ritchie, had caught the bug. They had tasted what a sophisticated multi-user operating system could do, and they weren't ready to go back to the old way of doing things. Thompson, in particular, had been working on a space travel simulation game on one of the lab's computers, and when Bell Labs exited MULTIX, he suddenly found himself without a machine to run it on. So he did what any reasonable person would do. He decided to write an entirely new operating system. Working nights and weekends on a discarded PDP-7 mini computer that was sitting in a corner of Bell Labs, Thompson built a stripped-down, elegant version of what MULTIX had tried to be. He kept the good ideas, the hierarchical file system, the idea of a shell that interprets commands, and he threw out everything that made MULTIX slow and complicated. He called it Unix, a pun on MULTIX, and it was later spelled with an X. What made Unix special wasn't just what it did, but the philosophy behind it. Where MULTIX tried to be everything at once, Unix was built around a simple idea. Make small, focused programs and let each one do one thing well and let them talk to each other. That idea, known as the Unix philosophy, would quietly shape software development for the next half century. But to write Unix, Thompson needed a language. Keep in mind that this was a simpler time to create a programming language. Computer instruction sets were smaller, memory limitations prevented compilers from being massive and complex. So Thompson had been working with BCPL, a programming language with its roots in Algol 60. And he essentially took BCPL, stripped it down, and adapted it to his taste, and he called the result B. B worked fine for a while, but it had a fundamental problem. It had no concept of data types. Every piece of data was just a machine word. This is where his friend Dennis Ritchie steps in. Ritchie took B, added a type system, added some other features, and named the result C, simply the next letter in the alphabet. C, released around 1972, was a revelation. It was low level enough that you could use it to write an operating system, but it was high level enough that humans could actually read and write it without losing their minds. And for the first time, you had a language powerful enough to build serious systems and portable enough that the same code could run on different machines because you only had to rewrite the C compiler, not the whole program. C became the language that an enormous amount of the world's software would be written in for the next few decades, and syntax lives on directly in C++, Java, and JavaScript, and lots of other programming languages. If you've ever written a for loop with curly braces, you are writing in the tradition of Dennis Ritchie. Bell Labs distributed Unix freely to universities for educational use, which turned out to be one of the most consequential decisions in the history of software. The computer science students learned to program on Unix systems, absorbed its philosophy, and went on to carry it with them into their careers. Unix became the shared cultural bedrock of an entire generation of programmers. All the while, a different user interface solution was being developed at a company specializing in photocopier computer technology. Xerox had established a research center in Palo Alto, California, known as Xerox PARC, and had quietly built some of the most forward-thinking technology of the era. Among other things, they had invented the graphical user interface. Instead of typing commands into a text prompt, you would see windows on a screen, move a cursor with a mouse, and click on icons. In 1979, Steve Jobs visited Xerox PARC. He saw the GUI and immediately understood what it meant. Apple shipped the Macintosh in 1984 with a full graphical interface, and suddenly the idea of a computer for ordinary people who didn't want to memorize commands became real. The U.S. government was also investing in computer technology once again. DARPA, the U.S. Defense Advanced Research Projects Agency, was running an experiment. They wanted to know if computers at different universities could talk to each other over a shared network, not by sending physical packages or files of tape through the mail, but in real time over telephone lines. The resulting network, ARPANET, connected 4 universities by the end of 1969: UCLA, Stanford, UCSB, and the University of Utah. The big conceptual breakthrough that made it work was packet switching. Instead of dedicating a whole telephone line to a single conversation, you break the data into small chunks called packets, route each one independently through the network, and reassemble them at the destination. It's more efficient, and crucially, it's more resilient. If one path through the network goes down, the packets just find another route. For most of the 70s, ARPANET was essentially a clubhouse for researchers and academics, and the general public had no idea that it existed. In 1981, DARPA released a report on the project stating, just as the telephone, the telegraph, and the printing press had far-reaching effects on human intercommunication, the widespread utilization of computer networks, which has been catalyzed by the ARPANET project, represents a similarly far-reaching change in the use of computers by mankind. Meanwhile, the business world was about to be turned upside down by a machine you've probably heard of. Also in 1981, IBM released the IBM personal computer. Now, IBM, as you know, was not a company that did anything small or impulsive. They were the mainframe people. But they had watched companies like Apple start selling computers directly to consumers in the late 70s, and they realized that the personal computer market was real, and they were already behind. This was the age of enthusiasts starting computer companies in their garages and trying to create killer apps to sell their PCs. In an uncharacteristic move for such a conservative company, IBM decided to build their PC quickly using off-the-shelf components from other manufacturers rather than designing everything in-house. For the operating system, they turned to a small company in Albuquerque called Microsoft, run by a 25-year-old Harvard dropout named Bill Gates. The thing is, Microsoft didn't actually have an operating system to sell them, but Gates had heard that a local company called Seattle Computer Products had written one called QDOS, which stood wonderfully for Quick and Dirty Operating System. Microsoft bought the rights to QDOS for $50,000, cleaned it up and renamed it MS-DOS, and licensed it to IBM. This was one of the most important business deals in the history of the industry. And the key detail is this: Microsoft licensed MS-DOS to IBM. They didn't sell it outright. IBM thought the money was in the hardware, but Gates understood that the money was in the software. Because IBM had built their PC from standard off-the-shelf parts, other manufacturers could make exact copies of the machine, and they did, by the millions. And all of them needed an operating system, and Microsoft was right there, ready to sell them one. Across the world, a 21-year-old student at the University of Helsinki got a loan from his grandparents to buy one of these fancy new PCs loaded with MS-DOS. This is Linus Torvalds at college studying computer science. He became familiar with Unix and its philosophy, so naturally when he used MS-DOS, he found it limited and toy-like. And frustrated by the limitations, he decided to build a new operating system for it in his own vision to be like Unix. More on this later. Microsoft saw that Apple had introduced the world to graphical user interfaces with the launch of the Macintosh, and in 1985 they shipped the first version of Microsoft Windows, a graphical layer that sat on top of MS-DOS. It wasn't great at first. It took until Windows 3.1 in 1992, and really until Windows 95 before it truly took over the world. But the direction was clear. The future of computing had pictures in it, and that meant that hardware had to keep up. Display monitors had to get sharper and faster. Graphics cards, dedicated processors for drawing images on the screen, began their own rapid evolution. If you wanted to render complex images in real time, as you might in a video game, you needed special hardware that could do an enormous number of simple calculations simultaneously. And this was the birth of the parallel processor in the consumer market. Rather than one very fast processor doing things one at a time, you had hundreds or thousands of simpler processors doing things all at once. Now let's take a look at computer networking again. ARPANET had evolved. Universities had adopted it widely, and it was connecting more and more isolated networks into one global interconnected network, an internet. And in 1991, the right man in the right place at the right time, Linus Torvalds, released his hobby project operating system onto the internet, Linux. Also in 1991, a British physicist at CERN named Tim Berners-Lee released something new on top of the internet, the World Wide Web. The internet already existed as a network of computers, but what Berners-Lee added was a system of documents that could link to each other across that network using a language called HTML and a transfer protocol called HTTP. And in 1993, a team at the University of Illinois created Mosaic, the first web browser that could display images alongside text. And that was it. The general public suddenly had a window into the internet. Then came the gold rush. Everyone could see that the internet was going to change commerce, communication, and culture, but nobody was quite sure how or how fast. Venture capital poured into any company with a .com in its name, and companies with no revenue, no clear path to profit, and sometimes no real product were valued at billions of dollars because they had a website and a dream. The NASDAQ index climbed and climbed through the late 90s, and in popular imagination, hackers became a romantic figure, the brilliant misfit who could bend the digital world to their will, which Hollywood was delighted to exaggerate. Films like Hackers and The Matrix captured the genuine cultural feeling that there was something new and electric and slightly dangerous happening in the world of computers. Then in 2000, it all came crashing down. Companies that had never turned a profit ran out of money. The NASDAQ lost nearly 80% of its value over the next 2 years. The .com bubble had burst, and a lot of early internet companies just disappeared. But the infrastructure survived. The fiber optic cables were in the ground. The protocols worked. The audience was there. And out of the wreckage of the bubble, more careful, more practical companies would build the actual internet economy. But that's another story for another evening. So it's time to wrap this up. What the bubble had also created was an enormous appetite in American culture for the idea of computing as a skill for everyone. If the internet was going to be the platform for the economy, the logic went, then everyone should understand how it worked. This became the Learn to Code movement of the 2000s and 2010s, a national conversation about whether programming should be as fundamental a skill as reading or arithmetic. Whether that conversation produced the right answers is still being debated. But it reflected something true. Software, which had started as the exotic concern of mathematicians and military engineers, had become a medium through which ordinary people lived large parts of their lives. The history of software, in the end, is the history of humans, finding more and more ways to offload thinking onto machines so that humans could do more thinking. And then I would have liked to create QR codes. I didn't quite have the time, though, but these are some great resources if you want to continue learning about computer history. So I'll open it up for questions if we got time.
We don't have a mic this month to pass around, so feel free to just raise your hand and he'll call on you. And then to make sure that the question gets in the recording, he'll repeat it again in the mic we have up here. So ask away.
You talked about Linux, but you skipped an entire GNU, and you skipped over GNU entirely, and I feel like that's like a really important part of the history.
Yeah, there's a lot of things that I wanted to include, like SQL, like object-oriented programming, a whole bunch of things. Sorry, I didn't repeat the question. The question was, why didn't you include GNU in the history? And I would love to, research that and do a presentation on it, but just had limited time and decided that it wasn't a vital part of software history 101. So.
In a similar vein, what was your favorite thing you learned that didn't make the final cut?
My favorite thing that I learned that didn't make the final cut. The thing is, I included a lot of my favorite things.
Right.
I think there's this computer called Colossus, which a lot of people know about the Enigma machine, right? And how Turing cracked that. There's a movie about it. But even more secret, there was, like, the Nazis followed up with another cipher called Lorenz. And this kind of nobody British post office research engineer built this computer called Colossus very secretly, which cracked the Lorenz cipher. And that was not known about until like 30 years later. And I thought that was a great story.
How did you choose to draw the line between advances in hardware and advances in software? Because you brought up the Apollo guidance computer, and that's a huge leap forward in hardware, but also those hardware changes precipitated huge software changes. You could talk about the MOS 6502, like totally different instruction set, very different philosophy. That's a hardware change to a software change. How did you draw the line?
So the question was, how did I draw the line between hardware events in history versus software events in history? I tried to include only the hardware history that was really relevant to the software parts, but also like I did get a little bit distracted, and I included a lot of stuff about, you know, the Harvard Mark I fiasco. So it was kind of a mix of like what I thought was important context and what I thought was just interesting stories. Yeah, that's a great Apollo guidance computer. I thought the whole thing was very important to the history. So. Got one.
I think I'm just going to say everybody's struggling thinking of questions because it was a great story with an awesome story arc. And like, even though I grew up a 90s kid, like was aware of most of that, there was details in a lot of it that you plucked out that I wasn't aware of, you know, just really good content. I was going to ask, like, what did you leave out that you wanted to include? But other than that, I can't.
Yeah, I mean, I would have really loved to go into the, so I don't know if there was a question exactly. Yeah, I don't know if there was a question exactly, but I did want to go into more of the late 1900s software advances, because, like, you know, new programming languages and how that evolved, I thought was probably going to be really interesting, but that could be a whole hour talk on its own. So
that might be more current 101.
Yeah,
course.
it's not like
The history.
Yeah, the whole history of computers. Do we have one more? Oh, that's okay.
I'm sorry, one more. So do you have anything to do with education? I'm sorry, I forgot what you said you did.
Do I have anything to do with education?
Like on any level, other than this.
I mean, I'm just a Expedia software developer with an interest in this stuff. I was a camp counselor that did some teaching in photography to Boy Scouts at one time, so I got a little bit of experience in teaching. So, not much.
Just curious. You said you thought this should be a topic, software history. When you first said it, it was kind of like, I don't know, but after seeing it and just where we are today, okay, yeah, that's like beyond vintage.
Yeah, and
years.
when I Googled it, it was like there are software history classes out there. It's very rare, though. It's definitely not in high school. It's, you know, not at Missouri State, as far as I know. So, yeah, I think it's going to grow as a field of study.
I remembered my question.
Yeah.
With that in mind, if you're hoping to teach people in the future about the history of software, what are your opinions on software preservation? It's very difficult to find ways to preserve software for machines that didn't even exist. It's nice that we have a diagram of this program for the analytical engine, but we have no analytical engine to run it on. There's do you preserve software when the hardware goes away?
Okay, so yeah, the question is, how do you preserve software when the hardware goes away? And with old computers, of course, it's easy because they were slower, and we can just emulate them today on modern, faster computers. But if you know about Moore's law, we're kind of approaching a point where we can't make faster Turing machines, and we can't endlessly emulate things. And so it's like there are pieces of abandonware which are things that are no longer supported, that exist on just a few people's computers. They're not officially being sold anymore and that sort of thing. And right now it's really just hobbyists just doing their best to port things to newer systems. But in a lot of ways, old software disappears, just like old movies, old music. It's just like if it doesn't have the people to support it, it disappears.
I got a question.
Yeah.
So you just brought up Moore's Law,
Yeah.
which is nearing its end. And I know this talk was about the history of software, but in your own opinion, where do you think it's going, especially with the advent of AI and potentially quantum computing and the end of Moore's Law? Where do you kind of see? Because some of the things you brought up, that lasted 50 years, that still people are using today.
Mhm.
So where do you see it going?
The question was, where do I see software going in the future? Of course, nobody has a crystal ball, and so whatever I say now, I'm going to regret in 5 years, I'm sure. Of course, a quantum computer is something that operates outside the bounds of Turing machines. So I'm not sure how many people are familiar, but Google recently made an announcement that encryption is going to be cracked pretty bad by 2029, and a lot of internet traffic that has been recorded over the years is suddenly going to be a quantum computer away from being decrypted. And so quantum computers, I think, generally are fascinating, and they are going to introduce new possibilities, especially as we discover more and more quantum algorithms for very specific tasks that I am not qualified to talk about because I just don't know enough about programming quantum computers. Besides that, I think, and this is unpopular opinion time, but the biggest operating systems are Mac OS, Windows, and Linux. And they're pretty big and bloated, and I kind of feel like sometime soon, there's gonna, just like how Multics got replaced with Unix, somebody's gonna, some team somewhere is probably gonna get fed up and be like, we're making a bare bones operating system. We're gonna just make it do what it needs. It's not gonna support all of the old software that people want. But I think that's probably going to start sometime in the near future, and it's going to catch on. That's my opinion. I don't know where that's going to come from. I couldn't do it myself. I mean, if I really cared about it and if I quit my job, maybe I could make an operating system, but I don't think. I'll go over here.
Okay.
Sorry, you, sir. Yes.
Okay. Thank you, Jason Klein. Just a comment regarding quantum compute. IBM is one of the forerunners in the quantum space, and as part of that responsibility, they see themselves as also the ones to help promote quantum security. Not necessarily security in the quantum space, but what can we do to protect ourselves now? You brought up a great point mentioning a lot of things that are being encrypted today probably be breakable in the next 5 to 10 years. They've helped produce quantum safe encryption that we can use now that is more resistant to quantum attack. So just FYI for people that are worried about this stuff, if you're worried about data at rest, worried about data on the wire, definitely take a look at that.
And to quickly reiterate, he was just talking about how there are new encryption algorithms being developed by IBM that are going to replace the old algorithms that are crackable by quantum computers. Yeah.
When did you start? What time frame did you start this with? Back in the Victorian?
It was like 1820. Sorry, the question was when did the story start? Around 1820. I think the first year that I mentioned was 1821 when Charles Babbage said, "I wish these things had been computed by steam."
So when it comes to history lessons, one of the questions I find most interesting is like the what if questions around very key big moments. So given that you've studied this, I'm going to ask the same question in kind of two different ways, maybe. Like, what are in this history some key moments where if people made different decisions, we'd be living in a very different world, for the better or worse, right? Like, this would have set software back 50 years, or would have bumped software forward 50 years, right?
Okay, so the question was, what could have changed? Like, what different decisions could have been made that would have pushed us forward, set us back in software development?
Or just give us like a very different world today.
Or give a very different world from today. I think it's hard to say, but one thing that I did notice was Howard Aiken and Alan Turing both knew about Charles Babbage, and that could have influenced how quickly computers were developed from like 1935 to 1945, because I just assume that when Howard Aiken went to IBM and said, "Hey, let's build a computer," he probably showed them Babbage's work and was like, "Look, like this could have worked 100 years ago," and then they probably gave him more funding to make a bigger, better computer out of the Mark I. At the same time, I kind of feel like with the dawn of electricity, like that was maybe a more major thing. Because relays and vacuum tubes were like the electromechanical components that like got everybody working in the space at the same time. And so if Tesla didn't exist, maybe it would have taken a little more time to harness electricity, and maybe that would have an impact on computers. That's the best answer I got.
It's not Brandon and I taking a month to make JavaScript instead of 10 days.
Oh.
Just kidding.
All right. Well, I don't see any more questions, so I'll hand it back over.
Give him a huge round of applause.